Okay, so thanks all for coming. Mental note to myself, if I ever organize an event again, don't sign up to be a speaker. It's too much stress. And if you do so, don't sign up for 3 talks, one after the other. But looking ahead, this talk, what's going to distinguish it is there'll be no math, but there will be some performance numbers measured, okay? And the next 2 talks after lunch, they'll be on 2 separate topics. There are going to be no numbers at all, but there will be math, okay? So let's start. I'll recall some things that I said in the introduction, but we'll steer away pretty quickly. So money started off as this human convention that was a limited physical resource, limited by nature, like seashells or gold. And by now we're very used to fiat money, money made up by decision of other humans, some trusted parties, and controlled by them, central banks. And so there's a trusted party that controls the monetary policy. And then we have cryptocurrencies like Bitcoin, Ethereum, Zcash, and there are more than 1,000 currently being traded. And the motto is, in crypto we trust. The limited supply is by consensus, which we heard a lot about in the past 2 days, but there's no trusted party. And my takeaway message about Bitcoin is that it's the first time some societal function which required a trusted party doesn't need one anymore. It's been replaced by some combination of economic incentives and algorithms and protocols. And for Bitcoin, that's of course money, but people are already talking about other things that you can decentralize. And now this raises a new problem that didn't exist as much, or we thought didn't exist, or there were other ways to solve it, and that's the problem of computational integrity. And that's going to be the focus of all of my 3 talks, and it's the focus of my research and the stuff I do. So what's the problem? How can the public come to trust the output of a computation? Suppose you know the computation. How do you know that the output is what some other party that ran the computation reported? And the point is that often a party that is running the computation and has the computer and the code and also the inputs is actually incentivized to misreport the output. And the problem gets bigger as the party becomes stronger. So with individuals reporting their tax returns, of course they would prefer to have a lower tax amount. Small businesses, but there's a bigger party above them that could sort of look at them or audit them and ask them to reveal information. It works pretty well. But as the parties become larger and larger, things like monopolies or governments, then the ability to audit them is much more challenging. And when they make statements, it's very hard to know if to know if they're correct. So for instance, if when the police or the FBI is reporting some computation on a forensic DNA database, do we know that this is the actual thing? Or when the IRS is announcing that you've been randomly selected for an audit, can we trust it's really the case? Who's going to audit them? And other cases are that even when the party that is executing the computation may be agnostic to the outcome, there are others who may want to corrupt it. I mean, if the police is running some investigation and there is a politician that's very well connected and knows he has something to fear, he may influence them. So the police may not care, but this other party may. Okay. So larger parties, stronger, it becomes a bigger problem. And Bitcoin's solution is a very interesting one. It's one of full transparency. Everything that's important or that you might fear could be used to do bad things is just displayed publicly on the blockchain. And you can re-verify everything from the Genesis block till now. The problem, of course, now is one of privacy. If you reveal everything, then how do you keep things private? And in the context of Bitcoin, it's financial privacy. But if it's a forensic DNA profile, how do you keep that information private, or in or in surveys, as Rafael was just talking about, or in auditing financial institutions, as Neha was talking. So, recasting the problem, it's the following. How can the public come to trust the output of computation while preserving financial privacy, or in general preserving the privacy of all kinds of inputs that go into that computation? And we heard all morning about the right answer for this. It's all kinds of cryptographic proofs, specifically zero-knowledge proofs, and they were famously invented in '85, Goldwasser, Micali, and Rakoff, and got a lot of respect, rightly so. Recently, and actually with the help of cryptocurrencies, are we seeing them starting to be adopted for general large-scale computations as opposed to very specific ones. So here's my take. We heard excellent descriptions by Rafael, or explanations of how do you get a zero-knowledge proof. Here's the way I explain it, let's say, to my mom or to a random person on the street. So we all are very well familiar with things like grocery receipts and restaurant bills. And what are they? They are a bunch of data that actually proves that we should pay the sum, right? So they are a proof of computational integrity. The grocery store is saying you really should pay 10 shekels because what? Because you can re-execute the computation and sum up all the items and see that you reach the value of 10. So you can re-execute and verify computational integrity of the sum, and this also sort of enforces the other party to not cheat, because its reputation would probably be compromised if it's known that it's cheating there. So this is a proof. Now, cryptographic or zero-knowledge proofs are very similar, but first of all, they are zero-knowledge. So they preserve the privacy of auxiliary inputs. So if the computation involved not only stuff I paid, but stuff that someone else paid, then the zero-knowledge proof would not reveal that, as opposed to a grocery bill. And another interesting thing is that they are universal, or Turing complete, or next complete. So it's not just for summation that you can get a proof, but for any computation, anything specified by a computer program, let's say running for t steps, you could get such a proof. And the last thing is that they are scalable. And I've recently started using this term, scalable, that actually means two things. Sometimes I call it fully scalable. So it means two things. If you fix a program and think about running times and inputs going to infinity, so asymptotically, and you let t be the number of cycles on this machine, could be a Turing machine or some other model, then what I mean by full scalability or double scalability is two things: that the verification time is actually exponentially faster than execution time. It behaves like a polynomial in the logarithm of t, so something like log t squared. So checking a computation is exponentially faster than running it. But to support this exponentially faster verification, the proving side, so the grocery store, would need to run for more than t steps. And the other side of full scalability is that the overhead is not too bad. So instead of running t steps, it runs t times some polynomial in log of t. And for those, and sometimes it's called quasi-linear running time. It's almost linear. And here are just some numbers. So suppose the number of steps is, ranges between 1,000,000 or 10 to the 6 and 10 to the, whatever it is, 9, 12, 15. So a peta is 10 to the 15, I think. And the running time for the verification in terms of number of cycles, even for a peta, for 10 to the 15 cycles, would still be only 2,500. This is not the running time of some specific system. It's just explaining, for those who forgot how logarithms work, what they look like practically. And the overhead and running time would be at most 2,500, even for a very large computation. So this is what these systems are known to be capable of asymptotically. And I just want to mention that this Full scalability is also very interesting in the context of the scalability discussion within blockchains, because the proving side works a little bit harder, but not too much harder. And then in return, all parties that want to verify can work exponentially faster. And in particular, they also need exponentially less information to keep, to know that everything's okay. So in particular, suppose, again, just using these arbitrary numbers, suppose that in order to compute the latest UTXO set for, let's say, Bitcoin or your favorite cryptocurrency, from the blockchain, starting from the Genesis block, would have taken you 1 petasteps cycles on your machine. Then a single prover could do the work for you and work not 1 peta, but 2,500 times 1 peta, which is more. But in return for that, all other nodes in the world could get a proof that's at most 2,500 elements long and work in 2,500 steps, like an SPV client, and for that amount of work, know that the whole blockchain leads to the UTXO set. And I didn't even mention now zero knowledge. So you could also throw in zero knowledge, but that's not necessary. Even just the scalability aspects of this are really, could be really beneficial for blockchains. Okay, so we discussed some of the core properties of these very impressive constructions that have been known theoretically for a long while. Now, a little bit about myself. So I'm a professor here at Technion, and I started way back during my postdoc, actually, doing theoretical computer science that was all about getting certain kinds of proofs related to these zero-knowledge proofs to be more efficient. Specifically, I was working on probabilistically checkable proofs. And this was very theoretical. Then, thanks to some nice funding that I got from the European Research Council, we started actually implementing them. And first, I had even students in 2008 implementing them. And then we things were moving forward, and we actually started having all kinds of prototypes. So I started going around, even giving talks, saying, oh, this is really helpful for standard stuff. And at that time, I heard, like many others, about Bitcoin, but it didn't really ring a bell. And then just before I went to speak at the Bitcoin San Jose conference, I had this other eureka moment, which is something like this. If you talk to trusted party folks and you say, oh, we have this thing like zero knowledge and proofs, and like they're very succinct, so you'll spend most of your time explaining what they are and how they work and why would someone want them. And whenever you talk to decentralized folks, they would immediately just say, oh, cool, where's the code? And what's its running time? How do we use it? Don't tell me about applications. I'll tell you what could be done with that. And it was just this big difference between like standard worlds that work with big businesses and trusted parties and the decentralized world. And it still is, I think, this case. Maybe big businesses are starting to move over. But if you pause and think about it for a minute, the trusted party model is actually not bad. It's very good. And if you have a trusted party, and we all have a lot of trusted parties, that's good, the whole notion of asking for proofs from both sides is kind of, you could, but it doesn't really make sense. With respect to your bank or anything you already trust. Okay, you could, but on the other hand, if you're in a decentralized world, and I probably don't need to tell most of you sitting here, then it's all about getting proofs and assertions from parties that you don't want to assume that you know or trust. Okay, good. So at the same time, there was a team from Johns Hopkins that presented ZeroCoin, which was using sort of a limited kind of zero knowledge based on RSA accumulators for doing decentralized mixing. And so they had already some very nice application using not universal technology, and we were developing this universal technology and looking for applications. So we sort of teamed up, and it led to the Zero Cash academic paper. And then, in theory and practice are very similar, but it's, of course, a very big difference, and thank God Zuko and his wonderful team agreed to take this on themselves. So I ended up, along with all my co-authors, being founding scientists of Zcash, And you heard from Zuko, you'll hear more. Okay, so let me tell you what Zcash does. Again, no math, just something very, something you can try to explain to your mom. I'm not sure my mom actually would understand this, but some moms would. I love my mom very much, but okay. So in Bitcoin, Alice has some crypto idea, say this red-looking number, and Bob has his own ID, and then the transaction just says transfer, money from Alice to Bob. But the point is that when Bob is going to spend the money, he's going to use the same reference point, and now everyone can start connecting the dots, okay? And that's a problem. So Zcash, the solution of Zcash, and again, I'm mucking up a lot of the details. Zuko explained it to a deeper extent. But the basic idea is that instead of taking the transaction and saying Alice, Bob, sum, you take that text and let's say you encrypt it. I'm putting encrypt, you actually use a commitment scheme, but similar thing. So now it's encrypted. So what you actually see instead of the transaction is something encrypted. That's fine. So hiding the information is very easy. The real problem is that of computational integrity. How do we know that the encrypted message there hasn't done bad stuff, like multiply the amount of, by 10, where I didn't have it? And that's exactly where the proofs come in, okay? And the particular kind of proofs are these marvelous constructions, ZK SNARKs, actually starting with this wonderful suggestion by Professor Yuval Ishai, sitting here, with Rafael Ostrovsky and Eyal Kushilevitz, another faculty member, Technion, with a lot of improvements. And there are many, many citations that I'm missing out. This is not an academic talk. We had our own little addition at the end. So this is a particular kind of zero-knowledge construction out of many, many out there. Okay. Now, the really great things about ZK SNARKs, about this technology, is that you have very short proofs. I mean, they were 300 bytes. I think now they're like way shorter. I don't know, maybe 100. I mean, between 300 bytes and 0 bytes, there's not much room left. But they're shorter than 300. Let's say 100. Okay. And they have very fast verification, 10 milliseconds. So we heard about verification that's already in the microseconds, but it's already pretty good. And it's a universal or Turing-complete system, which means that any computation that you would like to verify, you could set up in a scalable way such a proof system. So that's really great. But I think the main criticism against ZK SNARKs, coming from none other than Zuko and myself and everyone who uses them, is that they require a trusted setup phase. And it's very, very hard to get it right. So again, I urge everyone to listen to this beautiful Radiolab episode where a reporter, Morgan Peck, is following Zuko as the ceremony is unfolding. It's really, really beautiful. But it's hard to do this time and time and again if you're not Zuko and his team of wizards. And it's enough to compromise such a trusted setup even once and then wreak big havoc on everyone who's using such a system. And another thing that may or may not be a problem is that if quantum computers actually reach scale, as IBM and Google are at least making announcements about, then these systems will again be compromised in the sense that you won't have security. It's not that you lose privacy, not backwards, but it does mean that you can't use them or trust them anymore. Just a little bit about Zcash as actually a cryptocurrency. So Zuko is here and he's going to talk a lot more. Number of employees, I think, has been going up a little bit. It launched on 28th of October. And the only thing I can explain about these charts is that on May 22nd, Zcash announced a proof of concept with JP Morgan Chase, and the price jumped. And another nice thing is that the price jumped only a few minutes or whatever, sometime after the announcement was made. So, anyways, this is the only thing I can likely explain about what's going on there. Okay, so the thing I'm going to talk about, again, now there's not going to be any math. The thing I'm going to talk about more in the next 2 talks is about a way to circumvent the trusted setup. And it's a new system that we call STARK. This is joint work with Ido Bentov, with Inon Choresh, and with Michael Ryabtsev, who's sitting somewhere there. And so the I mean, the pun on snark is, of course, intended. The greatest form of flattery is imitation. So a STARK, S is scalable, transparent, and argument of knowledge. Let's not go into that, something mathy. They're also post-quantum secure. And scalable as in fully scalable, meaning the prover running time is nearly or quasi-linear, and the verifier running time, verification time, is polylogarithmic. Actually, in STARK, it's actually in terms of arithmetic operations, the prover running time is going to be strictly t log t, so like the exponent in terms of arithmetic operations is 1, not 2. And verification time, I think, okay, I don't want to make statements I'm not sure about. But they're very efficient concretely. Now, just a few words about why is transparency in a proof system important. So it's first of all important for ongoing public trust because, as we discussed, even one leak would break the system. And the larger the party that is doing the computation, the more you would like transparency. Okay. And especially like if you want the government to start using zero-knowledge proofs or some huge banks, so you would prefer that they don't work in a trusted setup world because you would trust them less. They are strong enough to coerce leak or a compromise of a trusted key in certain settings. But there's another thing that's also very nice about transparency. So especially in the cryptocurrency world, there's all this collaboration going on, and people are developing code. I mean, probably Ethereum is the most amazing example of this. And so tomorrow you would like people to start building things with zero-knowledge proofs and people using them. Now, if it would be in a trusted setup world, there would be the proof building part, and people would need to examine the smart contracts and whatnot, but then you would need some other trusted party to set up the parameters. So you would really want a transparent system where someone wrote the code, someone reviews it. If you don't find bugs, which is of course a big problem, you can start using it, as opposed to say, no, now we need to run some ceremony or get some trusted keys. And especially if society is strong enough to actually push governments and large organizations to adopting things like proofs towards the citizen, then you really, really need transparent systems, I think. Okay. So how much time do I have? Just a lot, like 2 hours. Hey, I mean, I organized the conference, so you guys are staying here for 3 hours. No one's leaving. Yeah, exactly. No lunch for you. So now I want to give some numbers, and as numbers always go, especially, I mean, this is a system we actually built and wrote the code. So when I say we wrote the code, it's actually, you know, most of it is Michael and Ido and Inon, and they did an amazing job. So I want to give just a particular proof of concept that we actually built and measured. And so here's the story. There's a DNA database, a forensic DNA database that has in it, you know, as investigators go to crime scenes, they pick up DNA samples and then they reduce them in a laboratory to a sequence of 40 integers. It's called the CODIS system. Never mind, it's 40 integers in the end. It's 20 core loci is the number of repetitions from an STR thing.
Reliably serialized, there's a way to canonicalize it, always comes out in the same order?
I don't know. So in our it's a proof of concept. So we didn't actually talk to the FBI and tell them, or ask them, can you please tell us your format? What we did is we said, I mean, we do know that it's 20 core loci, and for each locus, it's 2 integers. So we said it's 40, and we did take the the search match algorithm as we could understand it from their website, but we didn't, go and actually talk to them and tell them and ask them, give us the exact format or the database. Of course, everything we did was just simulated data. Okay, so there's this database that has entries. Each entry corresponds to some DNA profile picked from some forensic scene, and so it's 40 bytes long. And suppose that someday the government is benevolent enough to agree to, let's say, post a hash of the database content daily on a blockchain. And this it's a hiding and binding commitment scheme, so, I mean, the government shouldn't really worry about any information being leaked from this commitment. Okay, so suppose we're in a world where this has already happened. And now, along comes someone who may be Andy from this film, or it could be the nominee for the next chief of police, and he may be suspected to be corrupt or have ties, and the public would like to know that his DNA profile does not match to anything in the database. So if this would happen today, the police would just say, don't worry, we checked it, everything's cool, right? But suppose we're fast forwarding to this world where there is already a published commitment, so we would like the police to say, we took a program that everyone knows, its code or pseudocode is written here, and it does two things. It gets, let's say, a hash commitment to the profile of Andy or of this chief of police, and it gets a commitment to the last DNA database. And what it does, it scans through the database, checking whether there's a match using the match algorithm for Andy, and along the way also computing the hash of the whole data set, and then comparing it to what was published, okay? So this is pretty much what a trusted auditor would do on behalf of the public if he had access to the database and wanted to verify this. But now the police is doing it on their own, or the FBI. So this is the program we actually implemented with, again, our understanding of the way the DNA match algorithm is done. It's not a simple, string match. There's some notion of that's a little bit complicated. Okay, good. And now here's some running times that came from. So the top is the prover side, and the prover side we ran on a pretty large server that cost about $10K 2 years ago. So it has 32 cores, and the main thing, it has half a terabyte of RAM. And let's see what happens with the prover. So what we're doing here is we're scaling the number of profiles all the way up to 1 million. At the 1 million we stopped. It took us a day for the prover to compute on this machine. So 1 million profiles is actually 40 megabytes of the file size. And what you see here is the overhead, the multiplicative overhead in proving time over naive execution. And so you see it's about 50,000 times slower to generate the proof. And then there's this big jump at around 9K. And here we have something that's a little bit like, it's the proof size, not the proof size that's sent to the verifier, but something internal. There's an interactive Oracle proof of proximity. It's something internal used by the prover. The main thing is that as long as you can keep all of this proof in memory or in the RAM, you'll be running pretty fast. And then what happens is that around 9K, you see we're just going from half a terabyte to 1 terabyte, and then we start using the swap, and so it goes from 50,000 overhead all the way to like 250,000. So I think what this indicates is that suppose we have better hardware, you would probably see something that's going a little bit slower for a while, or if we have better engineering to use swap memory or design things better. Okay, on the verifier side, things are much nicer. So the verifier can be simulated up to large numbers, and we could even simulate a verifier up to 149 billion entries. So it's 40 times larger in terms of data information. And you can see that the prover running time as these things, this is a logarithmic scale, and this is a linear scale. So the prover time, the verifier time is climbing very slowly, starting from 20 milliseconds to 80 milliseconds. And here we have the ratio of verification time to naive execution time. And what you see is that For the first time, for a scalable system, actually we have that naive verification is faster by a little bit than naive execution. So verification is faster at 80 bits of security. And of course, as you get better hardware and faster things, the speed up is going to be more noticeable because of this scalability. And then you see the same thing about here is the argument size, the actual amount of information that the verifier sees. It's not what's here. And it also goes up pretty slowly. So for 150 gigabytes of information, it's about 1.2 megabytes of proof size. Oh, and an interesting thing is that most of it has to do with authentication paths for those interested, and the number of queries is very small. Okay. There are many other theoretical approaches to getting zero knowledge, and there are a bunch of attributes. I guess I want to sort of flash that in terms of things like universality, scalability, non-interactiveness, post-quantum security, STARKs sort of achieves all of them. But others come very close, and in several aspects are a little bit better. So here's another thing I want to show you. So here are some numbers compared to some other prominent systems. So here we have the SNARKs in blue. And another nice thing that I want to emphasize is this new work that I'm not sure if the write-up is already posted, but the yellow thing is a system called Ligero that is going to appear in CCS by our peers sitting here, 3 of them, Mutu, Karmit, and Yuval. Right, only 3 are sitting here. Okay, good, there's a 4th. So what you can see, and again, I should say it's very hard to compare apples and apples. So their system is really great for very small instance size, like things that you could use, let's say, in something like Zcash, like a small number of things. And even for the same sort of reference implementation that we academics, sadly, that's the only thing that we currently manage to sort of compare apples to, you see that it has the best prover time among all of these. The verification time of STARKs is, total verification time is best. What happens in SNARKs is that if you have the trusted setup and you think someone else, and you assume someone else did it, then verification is fastest. But if you're in a world where you don't trust that and you need to generate things, then it's not so fast. Okay, so I guess here what you should take away from this is that although I'm very fond of STARK, there's a whole range of different proof systems out there. So for all of you wanting SNARKs and STARKs and other ZK systems, there's there's a big range of things that you have not only theory, but also practical implementation. So you should talk to your favorite academic and get your ZK proof out there quickly. Lastly, I want to emphasize again the effect of scalability as it happens out practically. So let's talk about the compression time, which is just the ratio of verification time over naive running time, okay, as a function of the number of entries in the file. And the same thing you could talk about the space compression. So this is like related to scalability of blockchains. So the amount of data in the data set, like this DNA data set, but it could be a blockchain tomorrow, and you put that, but you divide it by the communication complexity that asserts to computational integrity. And here we have, again, just these ratios practically for STARKs over the example of the DNA system. So, and I'm repeating things that were shown. So as the data set grows larger, the prover works harder, but the savings for all the verifiers out there becomes more and more noticeable, both in time and in space. So this is most relevant to things like blockchain compression, right? Because something with a data set with 9 billion entries, you would get a savings of a factor of close to 1 million if you used a STARK. Good, so I want to conclude. Bitcoin's innovation, the first decentralized societal function, and removing the trusted party raises this big issue of privacy and integrity. Crypto proofs, like those used in Zcash, ZK SNARKs, Ligero, there are a bunch of others, they solve these problems. And I'm particularly fond of ZK STARKs. They're transparent, they're scalable, they're post-quantum secure. Two questions: what are going to be the next societal functions to be disrupted, and what can DK STARKs do for you? So in my future talks, there'll be no numbers, but there will be a little bit of math explaining what's going into constructing such proofs. Thanks.
Okay, we can maybe take 2 questions before we break for lunch. So raise your hand if you have something. Right here. Yeah.
So this is brand new.
That will be public when everything's...
I mean the code itself, not just the page.
When things were ready, meaning papers were peer-reviewed and published, you know, in libsnark, we posted it online using MIT license. We did the same for something called Psi that appeared in Eurocrypt, and I can send you links to it, which is it's scalable and transparent, but doesn't have zero knowledge. So, I mean, that's the past experience. Yeah.
All right. One more question, maybe? There's someone up there, I think.
We used our own server. I think, you know, I don't know. Like, Michael, do you want, if he's around, like... No, but like, why won't we? I mean, we use the, no, VLab we tried, or we... It's not something that we report yet. Yeah, okay.
All right. I think that's all for now. We'll be back at 2 after lunch, I suppose, and hear more Veli.